Hello everyone, this is Tusher working for Microsoft Research at Redmond as a research software engineer. Today I'm going to talk about our paper titled Whisper IoT in TV Widespread Spectrum. The deployment of IoT networks has rapidly increased over recent years to connect cities, farms, energy, and many other industries. Today, these networks rely on connectivity solutions such as LoRaWAN operating in the ISM bands. However, you might be interested in knowing how these mainstream IoT solutions are performing in real world. Here, we would like to share our experience with you. We have gained this experience from one of our earlier projects, FarmBase, that aims to enable data-driven agriculture. As a part of this project, we deployed sensors across a farm and aggregate data in a star topology LoRa network operating in 800 and 900 MHz ISM bands. We have made more than 30 research deployments in farms across the globe over a period of 4 years. Now, what did we get to know from this deployment? These farms can span tens of thousands of acres. The major challenge we have experienced in these settings is the relatively short range of the communication link compared to the size of a farm and sparsely deployed IoT clients. Consequently, we need to deploy multiple gateways to cover a farm, whereas deploying a single gateway may cost thousands of US dollars. Besides, setting up proper backhaul connectivity for a gateway is cumbersome in remote areas. It holds for several other industries, such as oil and gas, power grid, wind farms, and so on. As a result, we see the need for a longer range connectivity. Next, in the same context, we study the feasibility of monitoring plant stress using a camera in US 915 ISM band. Here, the problem is sending a large number of confirmed up packets as the ISM band suffers from the paucity of bandwidth. And here we see the need for a larger available bandwidth. In aggregate, we see the need for an IoT solution that can offer a combination of longer range and larger availability. To bridge the gap, we envision enabling IoT networks over the TV white spaces. TV white spaces are the allocated but unused channels in the VHF and UHF broadcast TV bands that can be leveraged for both high and low bandwidth data transmission. But why TV white space? As the TV band spectrum consists of lower frequencies than the ISM band, it facilitates longer range connectivity, which extends to tens of miles and even through some obstructions. In addition, in less densely populated areas, there are typically several unused TV channels available for the use by TV whitespace devices. In the aggregate, these available channels can offer a large bandwidth. Finally, lower TV frequencies even facilitate higher data rates for distant IoT clients, which in turn provides power saving on the IoT device. So we have the solution to our problem. Then what is stopping us from doing so? In the way of realizing this vision, there are several challenges. First, regulatory. While operating in a dynamic spectrum as the unlicensed user, the precondition is to ensure the protection of the incumbents from receiving harmful interference. Second, existing mainstream IoT MAC protocols, mainly designed for ISM bands, cannot make the best utilization of wide TV widespread spectrum in serving large traffic. Third, handling the dynamism in TV widespread channel availability and quality given the IoT devices are power constrained. The dynamism is mainly due to the occupancy by nearby licensed and unlicensed users. Finally, it is challenging to develop an efficient carrier sensing solution since our radios can communicate even when the signal level is below the ambient RF noise floor. Over the years, we have worked on devising Whisper, an end-to-end IoT network system over the TV widespread spectrum, which addresses both regulatory and technical challenges. We make the following contributions through our work. Our work supported FCC's decision to adopt regulations on narrowband widespread devices to operate in the VHF and UHF bands. Next, we design and develop an IoT radio that can operate in the TV widespread spectrum. Then we design a new MAC protocol for a star topology IoT network operating in the TV widespread spectrum. Finally, we make a large-scale real-world deployment of Whisper for more than 2.5 months. Now, Whisper system first requires a narrowband radio that can operate over the whole TV widespread spectrum. As a result, we design and develop a radio that continuously operates from 150 to 960 MHz. Here, we use LoRa modulation in the physical layer, which is very popular for long-range and low-power wide network communication. Unlike an off-the-shelf LoRa radio designed for narrow ISM bands, our design for a wider TV widespread spectrum requires careful consideration of avoiding leakage and harmonics in an adjacent TV channel or other licensed band within the spectrum. Now, using the Whisper radio as an IoT client device, we also need a gateway to enable end-to-end communication. This figure shows the architecture of Whisper gateway. The radios integrated with the gateway are referred to as base station radios and follow a similar design to the Whisper radio. The number of base station radios can be adjusted depending on the scale of the network. Next, as we mentioned earlier, existing mainstream IoT protocols are mainly designed for ISM bands and cannot make the best utilization of wide TV widespread spectrum in serving large traffic. Here, we design and implement FTDMA-based MAC protocol. Now, I will try to explain the protocol from very high level. In the figure, you can see the proposed FTDMA structure. We divide the T-axis into two dividing time units, periodicity quantum and scheduling quantum. The required periodicity of periodic traffic is basically a multiple of the periodicity quantum. Each periodicity quantum is further divided into an equal number of scheduling quantum. Scheduling quantum is the minimum time precision required in the scheduling. For communication, each radio is allocated at least one slot in this FTDMA system. A slot is a group of consecutive scheduling quantum. Next, I briefly talked about how the slots are allocated. First step of slot allocation process is scheduling quantum selection. This algo takes either periodicity as the input if the slot is periodic, or expiry if the slot is one time, such as a slot for event-driven data communication. The goal of this algo is to find a set of scheduling quanta that are not already allocated so that two communications do not collide. We use linear Diophantine equation at the core to find the collision-free quantum. The algorithm is optimized for serving maximum possible slot requirements. This helps Whisper in accommodating a large network with a single gateway. Next, we have the channel selection algo that is completely independent of quantum selection algo. It aims to optimally find the channel for new slot requirement complying with the FCC's 1% duty cycle limit for channel occupancy. Specifically, finding a downlink channel is challenging. A downlink channel might be assigned to multiple clients, and these assignments can collide in different combinations and outcomes. Furthermore, in a gateway having multiple base station radios, although the T-axis is separate for each base station radio, the F-axis is shared, and the channel occupancy is calculated in aggregate for all base station radios. To address this challenge, we propose binary counting based dynamic table on top of the linear differential equation. Here, we target to optimized utilization of bandwidth, yet complying with FCC regulation. The next challenge is the dynamic nature of the TV WhatsApp spectrum. First, the long distance between the gateway and the client brings about separate uplink and downlink channels having dissimilar quality at their corresponding location. Second, the IoT clients are power constrained. Hence, any extra transmission and carrier sensing activity by the clients for TV for spectrum management adds power overhead. Whisper addresses these challenges in two steps. First, by implementing spectrum awareness capability at the gateway. Here, the conventional approach of measuring RF energy in a narrowband channel as an indication of interference level is not viable, because the LoRa modulation enables frame reception even when the carrier signal level is below the ambient RF noise floor. To address this challenge, we design a spectrum sensing module. The spectrum sensing module locally generates RF signal with a controlled amplitude and combines it with ambient RF signals to determine the quality of a narrowband channel at the gateway. However, the carrier sensing at the client end would add huge power overhead. Here, Whisper enables spectrum exploitation approach to mitigate the effect of interference through dynamic channel assignment. In simple words, we use channel hopping and missing packet based bucket filling method for monitoring the quality of a channel. It does not require any additional frame transmission or carrier sensing on the client side. Now we talk about the real world deployment of Whisper. We have an ongoing deployment of Whisper on 8,500 acre dry land wheat farm in eastern Washington, which has been operating for over 2.5 months. Here, Whisper is used by the third-party users in collecting sensor data from 17 different fields for multiple data-driven agriculture applications. The deployment includes 20 IoT devices that communicate with a single gateway. Let's see the results of this deployment. First, we find that Whisper facilitates at least 5 times range improvement over LoRa operating in the ISM band. Next, the lower frequency of TV widespread spectrum facilitates 2 times less energy consumption than ISM band at a range of more than a mile. In addition, Whisper performed up to the mark in standard networking mode. We also evaluate the performance of Whisper under different types of interference in the real-world deployment. The dynamic spectrum access handler of the Whisper responded to the interference and triggered channel switching to avoid the interference. Finally, we focus on evaluating Whisper's capability in terms of scale. Since deploying a very large-scale network having hundreds of clients is challenging, we carry out the simulation. We simulate 3 network setups. First, Whisper MAC in TV widespread spectrum. Second, Whisper MAC in ISM band. And third, Pure Aloha in TV widespread spectrum, which is used by mainstream IoT solutions as the MAC. Comparison between S1 and S2 shows how the larger bandwidth of TV widespread spectrum facilitates scaling. And the comparison between S1 and S3 shows how Whisper MAC makes better utilization of the bandwidth compared to mainstream IoT MAC products. From the simulation, we found that with only 3 TV channels, Whisper can accommodate 5 times more traffic than ISM band. And Whisper MAC exhibits 8 times better performance than mainstream IoT protocols in accommodating large traffic. With this, I have reached to the end of my presentation, and I would like to summarize our work. Our experience from deployments in multiple countries has shown that mainstream IoT networks in ISM bands are bottlenecked by range and bandwidth. As a remedy, we have developed Whisper, the first IoT solution that operates over TV Wi-Fi. We make a real-world deployment of Whisper as an end-to-end IoT network system for more than 2.5 months. Whisper exhibits both range and bandwidth improvements compared to ISM band. At this point, I would like to thank everyone for attending the talk. We would appreciate your questions and thoughts.